Welcome to Fun Facts Online. In the time it takes you to stream this podcast, quadrillions of bits of data are flying around the globe, powering everything from your social media feed to the complex AI that recommended it to you. But what if I told you the very foundation of this digital world, the humble copper wire, is creating a massive traffic jam on the information superhighway? For decades, we've relied on electrons flowing through copper to move data. But as our need for speed grows, these copper connections are hitting a wall. They get hot, they consume enormous amounts of power, and the signal degrades quickly. The solution? To stop using electrons and start using light. This is the world of silicon photonics, a revolutionary technology that is forging the future of data transmission in light. Instead of better wires, we're building highways for light directly onto silicon chips, promising to redefine computing, communication, and so much more. The core idea is simple but profound. Replace electrical wires with tiny channels etched into silicon that act as light pipes. This isn't just swapping one wire for another. It's a deep fusion of light and electronics on a single chip, and it's already changing our world. So why is light the answer to our data problems? The modern world runs on data, and the amount we generate is exploding. Traditional copper interconnects simply can't keep up. They suffer from several physical limitations that become a huge problem at high speeds. First, there's frequency-dependent loss. Think of it like trying to shout across a crowded room. The further away you are, and the faster you talk, the more your voice gets garbled. With copper, the higher the data rate, the more the signal degrades. To fix this, you have to shout louder by pumping in more power, which generates a ton of heat. Data centers already consume a huge chunk of global electricity, and a lot of that is just for moving data around. Silicon photonics solves this by using photons, particles of light, which travel through optical waveguides with almost no loss and don't have the same resistance problems as copper. This means we can send data over massive distances, from one side of a chip to the other, or from one city to another, using far less power. Second, copper wires suffer from electromagnetic interference, or crosstalk. When you pack wires close together, their signals can interfere with each other, like hearing someone else's conversation on a bad phone line. This noise corrupts data and limits how much information you can send. Optical signals, on the other hand, are immune to this. Photons in different light pipes don't bother each other, allowing for incredibly dense and clean pathways for data. Together, these issues create a power wall, where the energy needed to move data starts to exceed the budget for the entire chip. Silicon photonics smashes through this wall. It offers massive bandwidth. A single optical fiber can carry tens of terabits per second, by using a technique called wavelength division multiplexing, where different colors of light each carry their own data channel. It's like having a multi-lane superhighway inside a strand of glass, thinner than a human hair. The power consumption is drastically lower, which means smaller electricity bills and a smaller carbon footprint. And because light travels so far with so little degradation, it enables longer reach and lower latency, which is critical for things like real-time AI and high-performance computing. Now, let's look under the hood. How do you actually build a circuit for light? This is where the magic of silicon photonics happens. An entire optical system is built on a single silicon chip called a photonic integrated circuit, or PIC. It's an intricate network of microscopic components that generate, guide, and detect light, all made using the same manufacturing processes that have given us cheap, powerful computer chips for 50 years. Most of these devices are built on a special type of wafer called silicon-on-insulator. It has a thin layer of pure silicon on top of a layer of glass. The huge difference in the refractive index between silicon and glass traps light inside the silicon layer, guiding it perfectly. This allows for incredibly small and efficient optical components. The wires of this circuit are called waveguides. These are the tiny channels, the light pipes, that guide light from one component to another. Making them perfectly smooth is critical, because any roughness can cause light to scatter and lose signal. But the real action happens in the active components. First, you need a modulator. This is the device that encodes our electrical data, our ones and zeros, onto a beam of light. Think of it as a super-fast optical shutter. The most common type is a Mach-Zehnder modulator. It splits a beam of light into two paths. By applying a voltage to one path, it changes how fast the light travels through it. When the two paths recombine, the light waves interfere with each other. If they're in phase, you get a bright pulse of light, a 1. If they're out of phase, they cancel each other out, and you get darkness, a 0. Another clever design is the ring modulator, a tiny racetrack of silicon next to the main waveguide. At a specific wavelength of light, it siphons the light off into the ring. By applying a voltage, you can shift that wavelength, effectively turning the absorption on and off to create your ones and zeros. These are incredibly compact and power efficient. Once the light has carried its data to the destination, a photodetector converts the optical signal back into an electrical one. Here's a fun fact. While silicon is great at guiding light, it's terrible at absorbing the infrared light used in telecommunications. So we integrate another material, germanium, onto the chip. Germanium is great at absorbing these photons and turning them into an electrical current that a computer chip can understand. Now, you might be wondering, where does the light come from in the first place? This is the single biggest challenge. Because of its atomic structure, silicon is extremely inefficient at emitting light. It's a great material for electronics, but a terrible one for making lasers. So engineers have developed clever workarounds under the banner of heterogeneous integration. The most common solution today is to use an external, high-performance laser made from a material like indium phosphide and then carefully pipe its light onto the silicon chip. A more advanced technique, called hybrid integration, involves bonding a tiny sliver of this laser material directly onto the silicon wafer itself, creating a high-performance laser right on the chip. Finally, to unlock that massive bandwidth I mentioned, we use components called multiplexers and demultiplexers. A multiplexer takes data streams on different colors or wavelengths of light and combines them into a single waveguide. At the other end, a demultiplexer separates the light back into its individual colors. This is wavelength division multiplexing, and it's the key to carrying enormous amounts of data. So where's this technology actually being used? The biggest and most important application today is in data centers and telecommunications. Every time you stream a video or do a Google search, your data is being moved by optical transceivers. As network speeds race towards 800 gigabits per second and even 1.6 terabits per second, silicon photonics has become essential. By putting the laser, modulator, and detector all on one chip, these transceivers are smaller, cheaper, and use way less power. The next big step is something called co-packaged optics, or CPO. This is where the optical chip is placed right next to the main processing chip, like a powerful network switch or GPU, on the same package. This shortens the electrical path from centimeters down to millimeters, slashing power consumption by up to 50% and reducing latency. It's seen as essential for building the next generation of massive AI systems. Speaking of AI, silicon photonics is revolutionizing artificial intelligence accelerators. Training large language models is incredibly power-hungry. But what if you could do the math with light? Researchers are now building photonic circuits that can perform the core mathematical operation of neural networks, matrix multiplication, entirely in the optical domain. This is done at the speed of light, with the potential for far greater energy efficiency than today's best GPUs. This field of photonic computing could pave the way for more powerful and sustainable AI. Outside the data center, silicon photonics is making autonomous vehicles safer. LiDAR systems create a 3D map of a car's surroundings, but traditional ones are bulky and expensive. By putting all the optical components onto a single chip, We can create solid-state LiDAR systems that are tiny, robust, and cheap enough for mass-market vehicles. Then there's the truly futuristic stuff, like quantum computing. Many leading approaches use photons as quantum bits, or qubits. Silicon photonics provides the perfect, scalable platform to build the complex optical circuits needed to generate, manipulate, and measure these photonic qubits. Because they can be mass-produced in standard chip foundries, it's a promising path to building the large-scale, error-corrected quantum computers we'll need to solve world-changing problems. Finally, this technology is poised to revolutionize medicine. The same principles that make these chips great for communication make them incredibly sensitive biosensors. By coating a tiny ring resonator with antibodies, it can detect specific biomarkers, like a virus protein or a cancer marker. When the target binds to the surface, it causes a tiny measurable shift in the light. This opens the door to low-cost, disposable lab-on-a-chip devices for point-of-care medical diagnostics, at-home health monitoring, and even food safety testing. Of course, the path forward isn't without its challenges. That laser source problem remains a key focus. Packaging is another huge bottleneck. Attaching optical fibers to a chip requires sub-micron precision, which is a slow and expensive process. And these devices are very sensitive to temperature, requiring clever thermal management to keep them stable. But despite these hurdles, the pace of innovation is breathtaking. Researchers are integrating new materials like thin-film lithium niobate to create ultra-fast modulators. Artificial intelligence is even being used to help design the next generation of photonic circuits. The industry is maturing, with giants like Intel and TSMC providing manufacturing, and a vibrant ecosystem of startups pushing the boundaries. Silicon photonics is no longer a futuristic promise. It has firmly established itself as the successor to copper in our data centers, and is now branching out to revolutionize computation, sensing, and quantum information. The road ahead involves solving deep challenges in materials, science, and engineering, but the foundation is set for a future where our digital world, and everything it enables, truly moves at the speed of light.